Okay, in this second example, we will go further from what we did in the previous example. Remember, in the previous example, we were able to calculate alpha, the level of the test, the probability of having a type 1 error, namely rejecting the null hypothesis while it was actually true. And we made use of a rejection region where y is less than or equal to 2. All right, from a sample of size 15. So we continue this example basically. So is our test equally good in protecting us from concluding that Jones is a winner if in fact he will lose? All right, so let's make sure we understand that. So is our test equally good in protecting us from concluding a wrong conclusion, I assume, that Jones is a winner while in fact he will lose? So what if the alternative is true, that Jones is not gonna be the winner, and you continue to support Jones, like you continue to think that Jones is gonna win? So this will be a type 2 error, and that's exactly what we want to calculate, the probability of a type 2 error. Suppose that we will receive 30% of the votes. Suppose that he will receive 30% of the votes in reality. What is the probability beta that the sample will erroneously lead us to conclude that the null hypothesis is true and that Jones is going to win? All right, does that make sense? So so the way we can calculate the beta is knowing what that true population parameter is. And so suppose that he will only receive, in reality, he will only receive 30% of the votes. What is the probability that the sample will tell us mistakenly, it will mislead us, and we will conclude that the null hypothesis is true and Jones is going to win, whereas the reality is totally different? You guys can resonate with that in the 2016 national presidential elections in the US. Remember that most of the polls were showing Hillary Clinton will win the election pretty easily. So, and then it turned out that things didn't happen that way. So, and a lot of speculation afterward followed. Some people suggested that the sampling was wrong. Some people, they came up with lots and lots of different theories about that. But it's always possible that when you do these statistical tests, that you can have an error, a type 1 or a type 2 error, and your goal is to minimize those errors. Anyhow, so the question is clearly asking for the beta, the probability beta, that the sample will erroneously will mislead us to conclude that the null hypothesis is true, that Jones is going to be the winner, and while in fact the reality is totally different. In the reality is that he only has 30% of the vote. So what is the probability of making a type 2 error? So beta is basically the probability of a type 2 error, and which is basically the probability of accepting the null hypothesis while the alternative is true. Accepting the null hypothesis when the alternative is true. And this probability, if you want, we can also write it as the value of the test statistic, value of the test statistic, in our case the y, the number of people's responses in that sample of size 15, is not in the rejection region, when the alternative is true. Okay, does that make sense? And it's very straightforward. So because we decided the rejection region is 2 or less, the not being in the rejection region, not in the rejection region will mean y is strictly greater than 2 when p is equal to 0.3 in reality. Well, obviously before the election, the true election, it's impossible to calculate the beta, right? Because we don't have access to that number. Only afterwards you can say if you have committed a type 2 error. All right, and that's again very straightforward. So we can use binomial distribution repeatedly. So it's basically a 15 choose 3, 0.5 choose 3. 3 people say they will vote for Johns versus the rest say no. 15 choose 4. Sorry, not 0.5 anymore, right? 0.3 we said. I'm still using the same numbers. Okay, so 0.3 probability that it will be favored by Johns, and 0.7 probability of rejecting Johns. Even though 0.3 probability of success 4 times, failure 0.7 probability and 11 times, and so on. You need to add up all these numbers, 15 choose 4, 15 choose 15, all the way up to 15 choose 15, 0.3 raised to the 15th power, 0.7 raised to the 0th power. So we need this sum. So if you add up all these numbers, and if I'm not mistaken, so this number should come out as 0.873. So what I will do is I'm going to show this on Excel next, so to make sure everybody is on the same page. But before I do that, let me just explain what we mean. So here what we are saying is, if we use a rejection region where y is less than or equal to 2, our test will usually lead us to conclude that Johns is a winner, even if p is as low as 0, even if the true probability is 0.3. Does that make sense? So our test will conclude, so I mean, it's not a good test in that sense, in terms of the beta. The beta is as high as 0.873, very close to 1. So in general, our test will usually lead us to a conclusion where Johns will be declared a winner, whereas in fact, he's far from being a winner. He can barely get 30% of the vote. Does that make sense? So we are very unlikely to commit a type 1 error, but extremely likely to commit a type 2 error. Does that make sense? So there is this trade-off between type 1 error and type 2 error. So because in the previous example, we were so focused on not committing any type 1 error, we were extremely strict in choosing our rejection region as small as possible. While this benefited us in terms of reducing the type 1 error, like rejecting the null hypothesis while it was true, but then it created a much bigger problem of, now the fact is, if in fact alternative is true, you might continue to accept the null hypothesis, and so that's a type 2 error. So you are extremely likely to commit a type 2 error. The probability that you will be committing a type 2 error is extremely high, very close. So therefore, in reality, we are somewhere in between, right? So we want to find a compromise between alpha and beta. So probably y being less than or equal to 2 as the rejection region is not a very good rejection region. So maybe we might consider to replace it with y equals less than or equal to, for instance, 4 or 5 even. So how will we decide on that? So we will explain that next, right? But beforehand, let me just go ahead and show the Excel results. So let me just connect my machine again. There we go. So if you move to Excel, oops, there we go. So we still have this this result. Let me just add another column here, so somehow it is cropping it out. Okay, there you go. So these were the results based on probability of Johns winning was 0.5. What if we change it to 0.3 instead? All right, so I'm just going to change it to 0.3. There you go. And then I'm going to drag this formula all the way down. This still adds up to 1. Obviously, if it were 0.3, the number of people in the sample who will support will be significantly lower, for you can imagine. It will be the highest at this, like at most 4 people among the 15 will be saying they will support Johns, if indeed Johns's overall within the population support for Johns was 30%. So what we are doing here, these numbers, so this thing has changed now. This is only 0.3. So this is the region where y is less than or equal to 2. Of course, we want y strictly greater than 2. So the probability as a result that y is greater than 2 is actually equal to whatever that number is. Oops. 1 minus whatever that number is, right? Oh my goodness. Equal to 1 minus that number. Hey, that's our beta, right? So that's exactly what we found for beta a few minutes ago, or the same thing here. Probability of y being greater than 2 is equal to 1 minus that number, which is the same thing again. All right. So so therefore, making these calculations in using Excel binom dist function is the key idea. Make sure you update it. The probability of success here is 0.3, right? It's kind of like I mentioned earlier. Before the election, it's impossible to know what the beta is. Why? Because we don't even know what is the what is the true value, like how many people will vote for Jones. We don't know, right? That's the whole point of doing a hypothesis test. But you guys see the trade-off between the alpha and the beta. So by selecting the rejection region extremely strict, we avoided having a type 1 error, because type 1 error was as small as 0.04, the probability of that, 0.004 I should say. But then it suddenly we suddenly have a huge beta, which is a problem. All right, so hope you guys enjoyed that. So next is, actually we can just okay, so let me stop this recording here. In the next 2 questions we will continue with that. So I will in the next video, because the videos are too long and it's not good, I guess. Let me see. Okay, so yeah, let's keep the videos short. So in the next video we will continue with this one. All right, so the answer to example 2 was the beta is 0.873, the probability of a type 2 error. Looking forward to see you guys in our next lecture.